Hello, I'll start our presentation on the anti-kernel exploit with Filesystems Fuzzer. First of all, let me briefly introduce the table of contents before starting. For the beginning, I'll briefly introduce our team and why we selected this topic. Then let me tell you how much the vulnerabilities affect various OS. Then I'll tell you in the order of triage and monitor, analysis crashes, and kernel exploitation. This project was conducted in the security talent training curriculum called BOB. There are 2 mentors and 1 PM, and I am in charge of the PM, and there are 3 team members. There are various file systems in the world. However, there are few cases of attack through the file system. This is because it is a weak attack model. At this point, you might think, isn't it not already root privileged to mount the image? However, if you put it in a USB and plug it into PC, it becomes auto-mount without any need for root privilege. At this time, if the corrected image is counted, kernel panic can occur. In this way, there was an attack model through USB, and we used JANUS. We developed a web monitor, analyzed 1 day, and successfully leaked memory. At last, we exploited kernel through 0 day. There are various OSs in the world, and there are many file systems used for each OS. File systems are large and complex, and making it difficult to find bugs. The file system is not suitable for auditing because the code quantity is best as follows. So we use a file system Fuzzer named JANUS. However, file systems are managed in the kernel space, so they can be a good attack surfaces. In addition, kernel interaction is possible in user mode. Each process access one file system. UF or race condition bugs can occur frequently. JANUS uses the Linux kernel library, which is called LKL. LKL is a library of kernel at the application level. It is generally used to lightly emulate the kernel with CANU. LKL is not a kernel. Sources are organized in Linux libraries separate from the kernel version. So the version of the LKL is always lower than the kernel version. The reason for using LKL is to recover quickly and attach AFL when fudging. Let me explain how JANUS works. First, remove the metadata from the image and mutate it. Second, mount with mutated image and metadata. Finally, operate a G-score that reads writes image files. This way, it operates at 2 dimensions. The file system looks for files by inode as metadata. Because metadata information is mutated and a crash occurs. Even if data is mutated, it is useless. After creating an image, system calls are called randomly to induce kernel panic. Therefore, it occurs when mount, sync, and unmount. Our targets are ext4, f2fs, and ptrfs, which are file systems that are auto-mounted in Ubuntu. Especially ext4 is auto-mounted in many OSs. As the most basic file system, there is metadata in the block based on inode table, and further we mutate this. ptrfs is light, efficient bit tree-based memory management and features automatic defragmentation. ptrfs is optimized for SSD and allows you can use it like a single SSD although multiple plugged in. F2FS is a file system optimized for NAND flash created by Samsung for flash memory. When the price is inquired by the actual Zerodium company, the price is set as follows, and the box they want should remain long. File systems are managed individually, so even if a bug is patched, it is reflected in the kernel rate. When applying the found HITBs, bug occur in various OS as follows. 3 in Ubuntu, and 4 in Bloom OS, and 25 in Harmonica OS, and 2 in Red Star OS. Then I'll show you that what causes kernel panic when USB is plugged in on a smart TV. The video shows that an existing flash is affecting the device you are using. The vulnerability is CV 2018-0108 79. And the target TV is a Samsung TV released in March 19th. The corresponding OS is Tizen 5. Victim is using a TV, and attacker with a malicious USB plugs the USB into the TV. Afterwards, kernel panic occurs, and you can see victim's TV freeze. If debugging is possible, I have seen the possibility of exploit. Reported it to version 5 of the kernel, and then uploaded it to 5.3. But there were many duplicate crashes and many invalid crashes. Therefore, Trace was developed and the crash file was changed to a mountable image, and the Kasan memory analysis plugin was installed there. Reproduced through Cameo, unit crash was classified according to the type of the bug and then saved in DB.
We built the Trace with Cameo and Python. On Trace start, firstly, the Trace Python script runs Cameo system and insert the crashable file system image. Secondly, Trace writes shell command to reproduce crash with input pipe. Thirdly, check the shell output command contains Kasan report with output pipe. Lastly, Trace roll back the Cameo system to clean state with Cameo monitor.
Efficiently checked and managed through the web monitor. You can remotely set and run file system fuzzers and check the crash lists. I will show you the monitor demo video. First, after pressing the plus button, write the fuzzer name and select the file system target and assign a core number. Then success notification appears and you can see the fuzzer running as follows. When you enter the crash path, there are a list of found crashes, and if you click to enter, you can see the detailed Kasan report. Then you click the image at the bottom to download. And you can check the running fuzzers on the dashboard and press stop to stop the fuzzers. You can also check the crash and crash types of the last 7 days on the dashboard. Below that, you can see the trace process status and a list of recent crashes. This is overall structure of the trace and monitor. The blue part is the automated way, and the green part is the part where we analyze or load code. The process is as follows. When Fuzzer finds a crash, it goes through triage and saves the Kasan report to DB, which can be managed efficiently through the monitor. We download the image from the monitor and reproduce it with Cameo, then analyze it with viewing the Kasan report, and load the exploit code. There are a total of 16 CVEs reported by us. Some of the reported CVEs will be explained by our team members.
Let me explain the CVE ratio we reported and detailed analysis of CVE. The following is the percentage of CVE we obtained per file system. The number of CVE that we reported was a total of 16, which is small, but it can be seen that they occupy a significant portion of the CVE relative per file system. This means that there is not much research on the vulnerability of the file system. It would be nice if additional research on file system was done in the future. So, since the final goal of our analysis of this crash is LPE, we internally scored each crash from 1 to 10 depending on the extent of exploitability. Now, I will explain the analysis of each crash type. First, null pointer reference vulnerability. ext4 mtdir function check if there are any files in the directory when executing a command that deletes a directory such as rmdir. The vulnerability is structure pointer called bh in the ext4 mtdir function. If the pointer becomes null, the location of B data is not calculated. If the next loop fails to find next entry during the loop of the function, if the latent value of the ext4 lead dir flow function becomes 0. Then the next loop is a null pointer reference vulnerability that occurs because the location of HB data is not calculated. For the exploit of the null pointer reference, you need to assign memory to low addresses. But, however, the zero address protection protects the null region. So, if you use the null pointer reference vulnerability, you can only do kernel panic. So, it is not much different from turning off your PC. So we gave 1 point for the vulnerability. Next, 19036 vulnerability. ptrf's root node function is a function to safely get the root node over tree. Vulnerability that occurs in ptrf's root node. This is a null reference pointer vulnerability that occurs when the return value of the RCU reference function is null. In the extent buffer structure pointer EB and cannot map to the location of EB lefts. Since this vulnerability is also a null reference pointer vulnerability, we gave it 1 point internally. Next is the Slab of vulnerability. PTRFS file system provide basic RAID for multi-device file systems. PTRFS supports RAIDs 0, 1, 10, and 5 and 6. And a notable feature in PTRFS RAID is self-healing redundant arrays. The self-healing redundant arrays is a function that finds and recovers error in files with duplicate copies. The vulnerability is the slab of the vulnerability that occurs in the index RBIO pages function of DTLFS. Striping in a RAID is a technology that can be used in parallel by storing data on one or more disks for performance improvement. And logically continuous data can be physically divided into multiple disks. In this vulnerability, the stripe offset is obtained using RAID map 0 to find the page index. In order to use the stripe function smoothly, the data is arranged and the striping value of the stripe is entered at RAID map 0. In order to obtain the page index from the vulnerability, it is used in bio page after obtaining page index using the starting address and stripe offset. As page index is larger than the array value of bio pages, an OB vulnerability occurs. There are three issues that must be overcome to exploit this vulnerability. First, the value of RAID map 0 is the starting value of the aligned stripe. And we need to know how this value come in. Second, we need to do heap feng shui to place the desired object in the adjacent memory of RBIO BIO pages. Finally, we need to change the BVC.BV page value to be overwritten to the value we want. We thought there were many problems to overcome, so we gave it 3 points internally. Next is 19449 vulnerability. First, F2FS manages the file system using 4 functions: checkpoint, segment information table, model address table, segment summary area. Checkpoint maintains file system status bitmap for NAT SIT set, a list of open inodes, and the summary entry of the currently active segment. SIT is a table that contains segment information such as the number of valid blocks and bitmap for the validity of all blocks. NAT is table of addresses for all node blocks. Finally, SSA is a summary entry that contains information about the owner of the data and node blocks. So, F2FS has checkpoint, SIT, NAT, SSA for each superblock and accesses file and directories using checkpoint and NAT. This vulnerability that occurs when signal or I value is incorrectly calculated in the init bin max MTime function, and a value larger than the size of the existing arrays is entered, and larger value is entered into getseg entry as an argument to retrieve the MTime value of the OB memory area. We need an arbitrary read-write to exploit the OB, but MTime variable is alone. We thought it would be difficult to exploit, so we gave 3 points internally. This is the last OB vulnerability. The variables old size and new size are set during the process of setting up an entry for the ext4 file system. These two variables are defined as size underbar t. Among these, the value stored in old size calculated through a function called LE32 CPU. Due to difference between the 32-bit and 64-bit data types, unexpected large value may be set. This is a vulnerability that occurs when there is no code to verify the value after that, and very large area from the first bar pointer memory is initialized 0. I wanted to use this vulnerability, but the memset itself was only 0. And in order to use another method, I had to consider the side effects that occurred when the value was initialized to 0. So we gave it 4 internal points. Next is the UAF vulnerability. The vulnerability is UAF vulnerability that was crafted by the RWSEM can spin on owner function. Call RCU read lock and execute the owner on CPU function to find out who the current owner is. If the log is free when the owner is in write mode, all data in the object is also deleted. But in the read mode, the data in the object is left even if the log is free. So it is used as core dump information. The owner on CPU function is handled by receiving a pointer. So if a free object enters, it malfunctions. Therefore, if we doing mount twice, we will have a problem due to the remaining pointer. When the first mount is performed, the owner in the semaphore is set to read permission and is freed when unlocked. At this time, when you mount the second, the free object will have a dummy value, and because it does not map with the RWSEM SEM leader variable, it goes into the owner on CPU function as it is. If we push in the heap value before the owner object is re-referenced again, we can exploit it if you control well the owner value. So we gave it 6 points internally. Next is 19447 vulnerability. This vulnerability is a UA vulnerability that occurs in the dump open list function inside the ext4 put super function. This is a vulnerability that occurs when the free inode is not scanned and print. The exact free point has not yet been analyzed, but the possibilities depends on how the free inode is put in. First, if the inode is still being used as a dangling pointer, it can be used by overwriting another value in the memory referenced by the inode. And secondly, if the free inode is used incorrectly only in the open list, only memory leak is possible. So we gave it 3 points internally. Next is 19448 vulnerability. This vulnerability occurs in the ptrfs try merge free space function. There are 2 pointers, right info and left info inside the function. It is a UAF vulnerability that occurs by manipulating the file system image, causing the 2 pointers to point to the same object, and after the right info object is free, referring to the same address. If we can put another object at the timing of re-reference of the free object, we can hijack the control flow of this function. However, the assembly code spacing was so short that it was difficult to push the object. So we gave it 7 points internally. Last, 19377 vulnerability. This is a vulnerability caused by the ptrfs queue work function. A free work queue comes into the function, and a vulnerability occurs when referring to WQ high. If you know free timing, then you can easily exploit it by pushing another object. Also, the work queue structure has a meaningful pointer. So if you have a triggering part of the function pointer, control flow hijacking is possible. So we gave it 7 points internally because it is very exploitable.
Before exploit this vulnerability, we need to know the general Linux kernel exploitation methods. In general, if we can write the arbitrary value to kernel memory with the vulnerability, there are 2 main ways to execute attacker's shellcode. The first way is overwriting the function pointer in kernel memory to execute the attacker's shellcode. If we overwrite the function pointer called on the kernel routine to address of article shellcode, and then call a syscall to the kernel to call the overwriting function pointer. The second way is overwriting the structure pointer in kernel memory to reference articles fake structure. If we overwrite the structure pointer referenced on the kernel routine, the article can write or call arbitrary address using kernel routine. So, to prevent these exploitation techniques, SMAP and SMEP mitigations are applied to kernel. Firstly, SMAP mitigation protects kernel from modifying structure pointers. If structure pointer referenced by kernel routine points user memory space, it occurs page port. Secondly, SMEP mitigation protects kernel from modifying function pointer. If function pointer called by kernel routine points user memory space, it occurs page port. These two mitigations controlled with CR4 registers 20 and 21 bits. So to bypass these mitigations, we should overwrite the CR4 registers 20 and 21 bits to 0. We can bypass mitigations by using return-oriented programming, aka ROP, or using wrong permission setting on physical memory called return to dir. The ASLR is a mitigation which maps process memory section randomly on each execution time. It protects process from articles memory referencing, and the same mitigation applied to kernel as KSLR. We need to know Linux kernel heap spraying technique because the vulnerabilities type is UAF, so we need to spray the kernel heap. Firstly, user can allocate kernel heap directly. User can access to kernel memory directly, so we must be specific syscall to allocate or free kernel heap memory. Secondly, allocatable block size is limited. Each syscall has different allocatable size, so there is some possibility of heap spray failure. Lastly, user process can use same syscall, so it shares same kernel heap memory, and there is some possibility of heap manipulation failure. Like this, 4 processes use specific syscall X, Y, Z, and the syscall allocates same kernel heap memory. To summarize, there are 3 rules to spray kernel heap. Firstly, the syscall must be user callable with low privilege. Secondly, the allocation size should be flexible. Lastly, the contents of heap block must be controllable. And we could find the sprayable syscall as follows. First syscall is message send. This syscall takes size and value to allocate kernel heap memory from syscall parameter. The heap block contains header on first 48 bytes. Second, syscall is send message and send M message. This is called text size and value to allocate kernel heap memory from syscall parameter, but the allocatable size is limited by socket type. In heap block, no header included. The last syscall is add key. This syscall takes size and value to allocate kernel heap memory from syscall parameter, but allocatable size is limited by socket type. On exiting the syscall, syscall frees allocated heap block in heap block 18 bytes header included. So we exploited all the CVE practice. It was ext4 UAF vulnerability like our UAF vulnerability. Left side is kernel debugger. Right side is test shell first. Check kernel data section is full with null bytes. And with exploit, we got kernel heap address and write arbitrary value to kernel memory. It checks same time kernel address is full with B bytes.
So we can start to exploit the vulnerability. First, let's see the root cause of vulnerability. The PTRFS file system uses kernel work queue feature to async operations. On user call umount command or unplug USB, the umount syscall starts and it calls close C3 function, free the work queue in PTRFS stop all worker function, and continue the close C3 routine. In the IPut function, it checks async option is on. And finally, calls PTRFS queue work function and reuse the print work queue structure. It sounds like easy. Just reallocate worker structure and follow the routine. But there are some problems. First, free and reuse of target structure happens in a flash. Secondly, the target structure is too small, as 16 bytes. So, we use race condition like allocation and find another heap spraying technique. And we could find another spraying technique in detecting a 17-year-old kernel bug. Vitaly uses a new heap spraying technique for 16 bytes size spraying. He uses ZXA syscall for heap spraying. It's a user callable, flexible, controllable, and no header included. But it destroys heap block on exit. When calling the syscall, user can set memory address of contents and allocate it. After allocation, it copies contents in user memory to kernel memory. But it destroys the kernel memory on exit. So, Vitaly uses user port FD syscall to prevent memory freeze. If user port FD set on page 2, memory read try on page 2 invoke page port and call pre-register handling function. And in handling function, call slip or while true to delay memory free. When calling this call, user can set memory address contents and allocation size. At this time, set user first FD on page E. After allocation, it copies contents in user memory A and to user memory A to kernel memory. And it continues to copy page 2, but page fault occurs by user first FD and slip the thread to prevent memory free. So we can reallocate target structure in the kernel heap successfully. The final task is analyzing the kernel operations with separate structure pointer. The .wq variable is corrupted and call btrfsq work function with it. Let's trace it. From the vulnerable function btrfsq work, kernel calls some functions to start worker thread, and the worker thread calls select task IQ function, but it's a function pointer in the corrupted structure. So this is the structure reference pointer at structure reference flow. If the SMAP mitigation is off, user can build the fake structure in user memory. And finally, set the select task IQ function pointer in the kernel shellcode, to the kernel shellcode. It's the DMESG printout for the RIP handling. RIP appears to arbitrary value. In here, multiple V. We will show you the demo video. User has mount permission to call umount syscall, and the SMAP and SMEP mitigations off. In the user shellcode, in the user shell, user can't open secret file, and after executing the POC script, some crash occurs. Finally, we got root shell, and we can open the secret file. Thanks for listening our presentation. Thank you.